Okay, geometry students, in this video today we're going to go ahead and start taking a look at lesson 1.2 and continue looking at the basics of geometry. We're actually going to continue to look, kind of take yesterday's lesson 1.1, in which we were dealing with looking for basic patterns, and we're going to continue that in a way, looking at some different terminologies as to what we were doing yesterday. So let's go ahead and get started. I want you to write down today's heading, if you would please. Inductive reasoning. Please copy that in your notes. Inductive reasoning, and then write down lesson 1.2 and also include today's date, please, so that you have really good organized notes. Okay, so inductive reasoning, lesson 1.2, and include today's date. Okay, let's go ahead and get started. I will tell you when I want you to write things in your notes. I will also tell you what's going to be on your test or quiz. This right here will be on a quiz or test, so please copy this in your notes. Inductive reasoning. Inductive reasoning, please copy this down, is when you look for patterns and make conjectures. Let me say that again. Inductive reasoning is looking for patterns and making conjectures. Let me show you something real quick, okay? In yesterday's notes, that's what we were doing. Remember how we looked, or yesterday's video, remember how we looked at this pattern here and we tried to find the next figure? And then we also looked at different lists of numbers and we tried to figure out what numbers would come next. Well, you didn't realize what you were doing, but you were actually making conjectures. And you might say, well, Mr. Earhart, what is a conjecture? And I'm going to show you that in just a second. But I just wanted to show you that just the other day you were looking at a pattern or a set of numbers or figures, and you looked for a pattern, and then you tried to figure out what would come next in that pattern. And what we call that inductive reasoning. You look for a pattern and you make a conjecture. Now, what is a conjecture? Well, please copy this in your notes. You need to have this in your notes. You need to know this for a test or a quiz. A conjecture is an unproven statement that is based on a pattern or observation. A conjecture is an unproven statement. It's not proven, and it's based on a pattern or observation. Now listen to me, students, please. Another word for conjecture, we're not going to use it in this class, but have you not heard of the word? I'm sure you have. Hypothesis. Sure you have. Make a hypothesis about something. It's an educated guess. Well, that's basically what a conjecture is. It's an unproven statement based on a pattern or observation. So the other day, that's what we were doing. When we said that our next two numbers in this pattern were going to be 21 and 24, these two numbers here were conjectures. We were conjecturing, or in other words, we were making an educated guess. Okay, and so that's what you were doing when you were trying to figure out what would come next in a pattern. Okay, so inductive reasoning is what you did yesterday. You look for patterns and then you guess and make a conjecture. Well, what is a conjecture? It's an unproven statement that is based on a pattern or observation. Okay, and so the conjecture is basically what you think comes next in a pattern, or what should happen next in a certain situation. Now remember, both of these terms are important. These will be on your tests and quizzes, okay? Now, I'd like you to copy this statement in your notes and leave a blank right here. Okay, go ahead and copy this down. The sum of any two odd numbers is blank. And I want you to make a conjecture, okay? I want you to make a conjecture as to what should come in that blank. Now, this is not going to be easy, but if you'll take really good notes, pay attention, and listen to me, I think you can do this, okay? So here we go. The sum of any two odd numbers is blank. Well, let's see. Let's pick two odd numbers. How about 1 and 3? By the way, sum means to add, okay? So we're going to add any two odd numbers. 1 plus 3 would be 4. Let's add two other odd numbers. 7 plus 13. Those are two numbers. And we get 20. Let's add two more odd numbers. Any odd numbers you want. 21 plus 9. Those are both odd numbers, and we would get 30. Let's add 3 plus 11. Those are both odd numbers, and we get 14. Okay, so what I'm doing is I'm listing out a bunch of what? Examples. Why would I do that? Why would I list out examples? Well, because I'm looking for a what? I'm looking for a pattern, okay? And then once I find a pattern, then I can figure out what goes in this blank right here. Okay, so here we go. The sum of any two odd numbers is blank. Let's see. I added two odd numbers right here and I got a 4. Well, 4 is a what? An even number. 7 plus 13 gave me out a even number. 3 plus 11 gave me out an even number. 21 plus 9 gave me out an even number. Now, let's see, is that really accurate? Well, let's think of a number line here, okay? Here's a number line, here's 0, here's the number 1. If I'm going to add, let's go ahead and put 2, 3, now watch this please students, 4, 5, etc. Watch this. If I start at an odd number and I go to even numbers, look what I'm doing. If I start with 1 and go to the next even number, how many spaces over did I go? 1. Do you see that okay? I went over 1 space. If I start here and go to the next even number, I went from 1 to 4. So I went over how many spaces? 3. If I went, let's put a 6 right here. If I went from 1 all the way over to the number 6, I went over how many spaces? 5. Okay, so it looks like to me if I take 1 plus 1, 2 odd numbers, I get an even number. If I take 1 plus 3, 2 odd numbers, I get an even number. If I take 1 plus 5, 2 odd numbers, I get an even number. And this pattern would continue. Now, I know you're probably saying, Mr. Earhart, I would have never thought of this on my own, and that's okay, students. That's why we take notes. That's why I give you homework. That's why you go home and do your homework and practice, okay? I will make the tests and the quizzes reasonable, but you have to have an open mind and try to figure these things out, okay? So, the conclusion I'm coming up with, or the conjecture I'm coming up with, is the sum of any two odd numbers is even. Okay? Now that's my conjecture. Okay? The sum of any two odd numbers is even. This is my conjecture right here, the word even. Okay? So there. I looked for examples, then I found a pattern, and then I made my conjecture, my educated guess, my hypothesis. Let's try another one. I know this is a little weird, a little different, okay? But remember, geometry is completely different than any other math class you've had in high school or that you will have in high school, okay? All right, copy this in your notes. The sum, that means we're adding again, the sum of the first n odd positive integers is blank. The sum of the first n odd positive integers is blank. Okay, now what that means is this. Once again, let's write down some examples and let's look for a pattern. The sum of the first n odd positive integers. Let's start with 1. 1 is an odd positive integer. And of course, if we have 1 and we find the sum of 1, it's just going to be 1. Now next, I would have 1 plus 3. That's called the sum of the first two odd integers, and that would give me 4. Now next, I would have 1 plus what? Look what it says, students. It says the sum of the first n odd positive integers. So odd positive integers. So 1 plus 3 plus 5. And what would that give me? 9. Okay, let's try it again. 1 plus 3 plus 5 plus 7. And that would give me 16. Let's try one more. 1 plus 3. Do you see what I'm doing? I'm just adding odd integers. That's all I'm doing. And every time I add another odd integer. So 1 plus 3 plus 5 plus 7 plus 9 would give me 25. Now, do you see anything special or any pattern about these numbers? Do you see anything special about these numbers or any pattern? Well, I do see a pattern and it's really difficult to see. So again, don't be discouraged. These are not easy, but just listen and take some notes and see if this makes sense. 1 is what we call a perfect square. In other words, we know the square root of 1. The square root of 1 is 1. 4 is a perfect square. The square root of 4 is 2. 9 is a perfect square because the square root of 9 is 3. 16 is a perfect square because the square root of 16 is 4. 25 is a perfect square because the square root of 25 is 5. Do you remember what a perfect square is? A perfect square is a number in which you are able to take the square root of that number and get out a regular whole number. And so 4 is a perfect square, 9 is a perfect square, so is 16, so is 25. These are all perfect squares because you can take the square root of each one of those and get out a whole number. And so here's my conjecture. Looking at these numbers here and trying to come up with a pattern, I'm going to make this statement right here, and please copy this in your notes. My conjecture is the sum of the first n odd positive integers is a perfect square. That's my conjecture. My conjecture is a perfect square. I'm just trying to finish the sentence, making an educated guess, using inductive reasoning, and making a conjecture. Okay, let's continue on. Let's practice, practice, practice. The product of any two odd numbers is blank. Now you can work ahead and try this on your own, or you can work with me, whatever you want to do. The product of any two odd numbers. Well, let's see. Let's take 1 times 3. Those are both odd numbers, and we got a 3. Let's take 3 times 7. Those are both odd numbers. I got a 21. Let's take 7 times 7. Those are both odd numbers. 49. By the way, students, I'm just picking these numbers at random here. Okay, as long as they're both odd numbers, it doesn't matter. 5 times 11. Those are 2 odd numbers. I get 55. Let's see. Excuse me. Let's try 9 times 5. That would be 45. Let's try 13 times 3. That would be 39. Both of those numbers are odd. So product means to multiply, and I've multiplied odd numbers, and I got out a 3, a 21, a 49, a 55, a 45, and a 39. And so I'm going to make the conjecture, it looks like to me, that anytime I multiply any two odd numbers together, I'm going to get out a what type of number? Here it is, right in front of you, an odd number. Okay, and that's a pretty good conjecture. Okay, so I basically made up my own examples here, and then I looked for a pattern, and then I wrote down my conjecture. Okay, again, just stay with me, take really good notes, practice, 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 and then do your homework really well, and I think you'll understand this. All right, now let's take a second and let's switch directions. Okay, let's switch directions. Don't write this down, just listen to me. When we use inductive reasoning and we make a conjecture, and by the way, remember, that's what we did here, here, here. Okay? 1, 2, 3. 3 times we used inductive reasoning and we made a conjecture. Will our conjectures always be true? It's very important you write this next sentence in your notes. Write this down, please. No, some conjectures are not true. And by the way, they might seem to be true. Okay? Think about this for a second. If I were somewhere able to find 100 Dalmatians, and I were to take 100 dogs, and you were sitting in a chair in a room, and I brought in one dog, then another dog, then another dog, and every dog that I brought in was a Dalmatian, you might come up with a conjecture that all dogs are Dalmatians. And that would be a good, smart conjecture if you did not know anything about dogs, because all that you saw were Dalmatians, but it would not be a true conjecture. So write this sentence in your notes, please. Some conjectures are not always true, okay? So sometimes you'll make an educated guess, and it just will not be a true conjecture. So please copy that in your notes. That would make a very good test or quiz question. Okay. All right. Now, this word counterexample, please write this in your notes. You need to know this. Copy this in your notes, and then I will show you what a counterexample is. Okay. A counterexample is an example that proves or shows a conjecture to be false. A counterexample is an example that shows or proves a conjecture to be false. Now listen, let's go back to my Dalmatian example, okay? You made a conjecture and you said what? All dogs are Dalmatians. That was your conjecture, okay? Now, do you know what a counterexample would be? It would be an example that proves that conjecture false. So all that I have to do is leave the room and come back in with a what? A German Shepherd. And as soon as I walk in the room with the German Shepherd, I just proved your conjecture wrong. All dogs are not Dalmatians. And how did I prove that? I used a what? A German Shepherd. Do you know what the German Shepherd is? It's a counterexample. Do you see now what a counterexample is? It's whatever you use to prove a conjecture false. Now, are all conjectures false? Of course not. Some conjectures are true, but some conjectures are not true. And when you prove a conjecture wrong, you use a counterexample. Okay, I hope that makes sense. Okay, once again, a counterexample is an example that shows or proves a conjecture to be false. Let's continue on and let's try to find some counterexamples. Okay, I would like you to write this problem in your notes. Okay, the sum of two numbers is always greater than the larger of the two numbers. Now that sounds pretty good. Here we go. You ready? 3 plus 5 equals what? Write this down, please. 3 plus 5 equals 8. And 8 is greater than your larger number over here. That's what this statement is saying. It's saying the sum of two numbers, in this case the sum was 8, the sum of two numbers is always greater than the larger of these two numbers over here, and that is not true. Okay, I mean it looks like it is, but in a second I'm going to give you a counterexample. So this looks good so far. 3 plus 5 is 8, and 8 is larger than either one of these two numbers. Okay, let's try 7 plus 11. 7 plus 11 is 18, and 18 is bigger than both of these numbers over here. 18 is bigger than 11, and 18 is bigger than 7. So it looks like this conjecture is true, but hold it, I just thought of a counterexample right here. 0 plus 3 equals 3. That's a counterexample because 0 plus 3 is 3. Is 3 larger than 0? Yes, it is. But is 3 larger than 3? No, it is not. And so I just proved this conjecture false by using this counterexample right here. Now you might say, well, Mr. Earhart, there's more than one counterexample. Well, sometimes there is. Over here, you could have used a German Shepherd, a Labrador Retriever, a Boxer, a Rottweiler, Doberman Pinscher, a lot of different dogs. Well, over here you can use more than one counterexample. You could say, how about this? -2 plus 4 equals 2. Is 2 greater than -2? Yes, it is. But is 2 greater than 4? No, it is not. So there's another counterexample. Here's another counterexample, 0 plus 9. 0 plus 9 is 9. 9 is greater than 0, that's fine, but 9 is not greater than 9. 9 and 9 are the same numbers. So this would also be a counterexample. Do you see what I'm doing? I'm looking for ways to prove this conjecture wrong, okay? And I did that 3 different times. Well, which one is the right answer, Mr. Earhart? Any one of these 3. Just any statement or example that proves this conjecture wrong would be a counterexample. Let's take a look at another one. Please copy this in your notes. all shapes that have all four sides the same length are squares. All shapes that have all four sides the same are squares. Now that sounds really good. Okay, it really does. I mean, go over, up. There we go. I mean, if all four sides are the same, it looks like a square. Okay, so it looks pretty good to me, but hold it. I mean, let's think about this for a second, okay? I'm not sure if I can switch this. I don't think I can. Let me draw it like this. How about this? How about if I drew, now watch this counterexample, okay? How about if I drew a length here of 2 inches, we'll pretend, and then a length here of 2 inches, and then a length here of 2 inches, we're pretending it's 2 inches, and then a length here of 2 inches. There we go. That's called a parallelogram. That is not a square. Okay, it looks like a square that someone stepped on and kind of smashed it in. It's also called a rhombus, by the way, and we'll contain your excitement. We'll learn all of that later this year. But just because a shape has all four sides, we're going to say 2 inches, 2 inches. Please copy this in your notes. 2 inches and 2 inches. Just because a four-sided figure has all four sides that are the same length, that does not mean you have a square. And this statement up here, it said a shape that has all four sides the same length has to be a square. And that is not true. And here's your counterexample. You just proved it wrong. You drew a shape that has all four sides with the same length, but it's not a square. That is not a square. Okay, I hope that makes sense. This is your counterexample that proves this statement wrong right here. Okay, let's continue on. If the product of two numbers is even, then the numbers must be even. Now, let me quickly put this in maybe easier words to understand. Product means to multiply. So it's saying if you multiply two numbers and you get out an even number, then the two numbers must have been even. For example, 2 times 4 is 8. Did I get out an even number? Yes. Are both of these numbers even? Yes. So far so good. It says if the product of two numbers is even, then the two numbers you multiplied must be even. Well, let's see. How about 6 times 10? 6 times 10 is 60. We got out an even number, and notice both of these numbers are even. But hold it, what about this? Here's a really good counterexample. Look at this. 3 times 12 is what? 36. Now look at your statement carefully. If the product or the multiplication of two numbers is even, so we multiply two numbers together, did we get out an even number right here? Yes or no? Is 36 an even number? Yes, it is. So if the product or multiplication of two numbers is even, then the numbers that you multiplied must be even. And that's not true. Look, here's the two numbers I multiplied, 3 and 12. Are both of those numbers even? No, they are not. This one is right here, but the 3 is not. Okay, so this would be a counterexample. Can you pause for a second and on your own go ahead and write another counterexample in which you have two numbers multiplied together that give you out an even number over here, but the two numbers that you multiply together are not even numbers? I'm going to wait about 10 seconds. I want you to try to think of one on your own. Okay, here's one you might have used. 7 times 8. 7 times 8 is 56, and we all know that 56 is an even number. Okay, so the product of two numbers is even. This is even. Then the two numbers that you multiply together must be even. Well, 8 is even, that's fine, but 7 is not. So this would be a counterexample that would prove this conjecture wrong. One more and we're finally finished. Okay, one more. Let me get a drink here real quick. If a four-sided shape has two sides that are the same length, it must be a rectangle. If a four-sided shape has two sides that are the same length, then it must be a rectangle. Well, students, I can right away think of a counterexample that proves that wrong. Look, let's say I go down, we'll call this 1 foot, and then we'll call this, in fact, I'm going to use the exact same line so we know it's the exact same length. Okay, so there's the exact same line right here, and now I'm going to turn it like this, and then put it right over here. There. Okay. All right. There we go. So, if a four-sided shape has how many sides that are the same length? 2. Well, we know this side here is 1 foot, and we're pretending we know that, okay? And this side right here is 1 foot, all right? Then the entire shape, it must be a rectangle. I'll just go like this. I'll just draw a figure way, I'll draw a line way over here, like that, and then connect those two real quick. And then draw that line right there, and then connect it, of course. Now, I have a question for you. Is this a four-sided figure? Yes, I have 1, 2, 3, 4 sides, okay? So if a four-sided shape has two sides the same length, well, this side here is the same length as this side here, okay? So if a four-sided figure, which is what I have, has two sides the same length, which is what I have, then the figure must be a what? A rectangle. And that's not true. I just drew a figure that has how many sides? 4, and it has how many sides with the same length? 2 sides, and it's not a rectangle, okay? This is a trapezoid. We'll learn that later, but it is not a rectangle. So this would be a good counterexample, okay? All right, I hope this has made sense today. Again, way back up to the beginning of your notes that we looked at today. What we looked at today is inductive reasoning, where you look for patterns and make conjectures. And a conjecture is an unproven statement that is based on a pattern or observation. And then later on we learn, this is so important right here, students, that some conjectures are not always true, okay? And if you prove a conjecture false, then whatever example you used to prove the conjecture to be false, we called that example a counterexample, okay? So then we went on and we proved some conjectures to be false by using counterexamples, okay? I hope this has made sense. If you have any questions at all, don't hesitate to call or email. Be sure and do your homework and watch the homework help video to help you.